Hello and welcome back to ZFC set theory. Today we're going over axiom number 4, the axiom of pairing. In English, it says that for any sets A and B, there must exist a set C whose members are precisely A and B. We can rewrite that more formally with quantifiers. For any sets A and B, there exists a C such that for all sets, the set is in C if and only if it equals A or equals B. This little symbol right here, by the way, means or. The symbol that looks like a V, you can remember it because if you turn it upside down and write a wedge, that means and, but this one means or. It should also be noted that the or in logic is an inclusive or, meaning it's still true even if both of these are true at the same time. It allows that possibility. Now, here's a question for you. This set C, is it unique? We know there exists some C that contains precisely A and B, but is it the only set C? And the answer is yes. Theorem 1, uniqueness of the pair. For any sets A and B, there exists a unique set C whose members are precisely A and B. In other words, this C here can be made to be unique. Let's prove this. Let A and B be sets. By the axiom of pairing, there must exist a set C with this property, namely that any set in C has to either be equal to A or B, and vice versa. If you have something equal to A or B, then it must be in C. To show uniqueness, we want to show that if there's another set C prime with the exact same property, then C prime has to equal C. Assume we have another set C prime such that this holds, that anything in C prime must equal either A or B and vice versa. If you're equal to A or B, then you must be in C prime. And what do we want to show? We want to show that C equals C prime. How do we show this? Well, by the axiom of extensionality, we want to show that everything in C is in C prime, and vice versa, everything in C prime is in C. Or in other words, we're going to show that C is a subset of C prime, and C prime is a subset of C. Let's show this guy first. To show that this is true, we got to show that everything in C is in C prime. So assume X is in C. We want to show that X is also in C prime as well. How do we do it? Well, if X is in C, then we must have this. Then X is A or X is B. So since X is an element of C, that tells us X equals A or X equals B. But since X equals A or X equals B, that tells us that X must be in C prime. So therefore, X is an element of C prime. So we showed that if anything's in C, it must also be in C prime. So this is true. Next, we want to show that C prime is a subset of C. How do we do that? Well, exact same logic. We assume that X is an element of C prime, and we want to show that X has to be an element of C as well. Well, since X is in C prime, then this part tells us that X has to be A or it has to be B. So X has to be A or X has to be B. But since X is A or X is B, this part tells us that X has to be in C. So X is an element of C. So that shows anything in C prime has to be in C as well. Since we prove both this and this is true, then by the axiom of extensionality, C has to equal C prime. So this finishes our proof of uniqueness. Since we proved now there exists a unique set having this property, we can invent new notation for it. For any sets A and B, define this guy to be the set containing precisely A and B. We're allowed to make this definition because we proved that this set was unique. A comma B is the same as this set, the set of all sets which are either equal to A or equal to B. Recall that if you have a set that looks like this, sometimes it exists as a set and sometimes it doesn't. However, in our particular case, we know that the set has to exist because we prove that there exists a set whose elements are precisely A and B. Now here's a remark. Notice there's nothing that says that A and B can't be equal to each other, right? So what happens if you have this set, A comma A? Well, that's just the set of X such that X equals A or X equals A. But this part can be simplified. If you're equal to A or you're equal to A, that's just the same as being equal to A. So this set is the same as the set of X such that X is equal to A. So this is a set with just one element, namely A. Therefore, we can define the singleton, the set containing just A, to be this, which can also be written like this. Okay, so that's one cool thing about the axiom of pairing is it allows us not only to form pairs like this, but singletons as well. And now here's an easy theorem, is it doesn't matter the order you write these A and B, they're the exact same set. Why is that? It's because this set is really this, and this set is really this, and we can see these two sets are exactly the same because saying you're in A or you're in B is the same as saying you're in B or you're in A. There's no logical difference. Here's another easy theorem. A set that looks like this is always a subset of a set that looks like this. Let's prove it really quickly. We want to show that every member of this set is also a member of this set. So assume X is a member of this set. Okay, well, if X is a member of this set, what is this set? This is the set of things which are equal to A, and there's only one thing then in that set, therefore. If X is in this set, that means X has to be equal to A. Now, if X is equal to A, that means X equals A or X equals B, right? So that means X is in this set, the set of things equal to A or equal to B, right? And what is this set right here? It's just A comma B in our alternative notation. So QED, baby. Now here's a warning. Not all books give the axiom of pairing as I've given it here, but some of them give a weaker version, which I'm going to call the weak axiom of pairing for now. It merely says that for any sets A and B, there exists a set containing A and B without specifying whether or not the set might contain some other garbage as well. Let's write that in quantifiers, shall we? For any sets A and B, there exists a set C, so that what? Well, C contains A and B. So that means A is an element of C and B is an element of C. So here's a question. If we were using a book and we took this to be our axiom of pairing, would we be able to prove the stronger version? And the answer is yes, we would, but we got to use the axiom schema of comprehension to do it. So let's prove both versions are equivalent. Obviously, if there exists a set C whose members are precisely A and B, then there exists a set containing A and B. So obviously, this one's stronger than this one. So all we got to do is show that if this axiom's true, then this one has to be true as well. Okay, so assume that this axiom's true, and assume we have sets A and B such that for some set C, A is in C and B is in C. The weak axiom of pairing says that there must exist a set with that property, but maybe C contains some other stuff as well. So how do we show that there is a set containing just A and B and nothing else? Well, consider the following set. Consider the set of elements of C such that X equals A or X equals B. We know that this set exists by the axiom schema of separation. Here is our P of X. But now look, this set can actually be rewritten like this. It can be rewritten as the set of X such that X equals A or X equals B. We can remove this X is an element of C constraint. Okay, and why is that? It's because whenever this condition is true, whenever you're equal to A or you're equal to B, well, then you have to be in C anyway, because if you're equal to A, then you have to be in C. And if you're equal to B, then you also have to be in C. So recall, whenever this condition here implies that you're in this set, then you can rewrite it removing this part. So this is the set containing precisely A and B. The axiom of pairing is pretty cool because it allows us to form other sets besides the empty set. So we already know that the empty set exists, right? But by the axiom of pairing, we know that this set exists as well. Remember I said earlier, you can make singletons using the axiom of pairing? Okay, so this is the set containing just one element, namely the empty set. So note that these two sets are distinct because this set, recall this notation, this just means the set of things which are equal to whatever inside. So these are the set of things that are equal to the empty set. So the reason these are not equal is because the empty set is a member of this singleton, but the empty set is not a member of itself, okay? And by the axiom of extensionality, two sets are equal if and only if they have the exact same members, so therefore these two can't be equal. We can also use the axiom of pairing to take another singleton, the singleton containing this set, so we can form the set containing the set containing the empty set. So this set exists as well. And by similar logic, you can show that this is distinct from this as well as from this. Another example is we could take a pair. We could take the set containing just this and this. So the set containing the empty set as well as this set, the set containing the empty set, this exists as well. So as you see, we can keep applying the axiom of pairing to form more and more sets. Now here's a question. Can we form a triplet? Can we form a set containing exactly 3 elements? And the answer to that question is not yet. And here's why. The reason we can't form a set with 3 elements is because when you apply the axiom of pairing, you get a new set that contains either 2 elements or in special cases, 1 element when those 2 elements have to be the same. However, it never gives you a set with 3 elements. So for example, if you have A, B, and C, you can make the pair containing A and B, and you can pair that with C, so you can have the pair containing 2 sets, namely this set as well as C. Okay, but still, this isn't a triplet because this doesn't have 3 sets. It only has 2 sets, this guy and this guy. Or similarly, you could form the singleton containing C by the axiom of pairing, and then make a pair consisting of this guy and this guy. And if you did that, you would get a pair consisting of our first element is this guy, A comma B, and our second element is this guy, the singleton containing C. Okay. But notice that this is still just a set with 2 elements, this guy and this guy. It'd be nice if we could just remove these inner brackets and get a triplet. It turns out we can actually do that, but we need another axiom to do it, the axiom of union, which is the topic of next time's video. Stay tuned.